All right, let's talk bacteria and doubling time. So suppose a single bacterium is placed in the bottle at 11 o'clock a.m. It grows and at 11:01 divides into two bacteria. These two bacteria each grow and at 11:02 divide into four bacteria, which grow and at 11:03 divide into eight bacteria, and so on. Now suppose the bacteria continue to double every minute and the bottle is full at 12 o'clock. We have two questions. How many bacteria are in the bottle at 11:37, and what fraction of the bottle is full at that time? So what fraction of the bottle will be full at 11:37? So let's do some visualizing. Gosh, good thing I'm no writing tutor or spelling tutor. So here's my bottle. Okay, all right. At 11 o'clock, put one little dude in there. Cool. At 11:01, 1 minute later, that's split into two, or just doubled. Another minute later, the amount has doubled again, so now there would be four. Another minute later, the amount has doubled again, so there'd be eight. A minute later, we've got another doubling, so now instead of eight, there are 16, because that is what happens when you double eight. If you do another minute later, you'd have 32. So if you double 16, you get 32. And then a minute later, you'd have 64. And then you'd have 128. It's going pretty far, and that's only a few minutes in. I think I just did what, 6 or 7 minutes in. So that's interesting. And they said that after 60 minutes is when it's full. So it takes 60 minutes for it to fill up. And I'm saying 60 minutes because they said this whole experiment started at 11 a.m. and then at 12 o'clock, right? Did it say 12 p.m.? It should probably say 12 p.m. Putting that in there, because this is a whole different problem if it's 12 a.m. if it takes that long. But let's say it's 12 p.m. So it takes 60 minutes, right? From 11 a.m. to 12 p.m., that's 60 minutes. So it takes 60 minutes for this whole thing to fill up. Okay, cool, great. So we had a little bit of visualization. That's my word of the day that I can't pronounce. Let's make a little table here to try to maybe make it a little more orderly. So I'm working with doubling time in minutes. So minutes, sure. I'm going to actually specify this as minutes past 11. You don't have to do this, but I'm going to do that because this whole thing starts at 11. And the minutes past 11, whether it's 1 minute past, or 2 minutes past, or 3 minutes past, that seems to determine how many bacteria are in the bottle at that time. So minutes past 11 o'clock. And I'm going to do number of bacteria. And my third column is going to be to test out a formula. Because we are doing doubling time, there is a pattern, we should be able to find a formula that we can use. All right, so at exactly 11 o'clock, so I'll change colors just to make it a little less overwhelmingly green. At exactly 11 o'clock, so 0 minutes past 11, there's one bacteria put in the bottle. Okay. 1 minute past 11, there are two now. 2 minutes past, we've doubled. 3 minutes past, doubled again. Just like we were talking about with the bottle drawing there. 4 minutes past, doubled again. 5 minutes past, doubled again. Now you could keep going if you wanted to, and you can go all the way down to 37. If you want to, go ahead. I'm definitely not going to recommend that because there is a little bit of a smarter way to do this, which is what we're going to do. Okay. So let's see if we can find a pattern here. Now we are doubling, right? It is doubling. So I know that 2 is going to be here somewhere. And I should also have some kind of exponent. All right. Let's see if I can set this up. I can find some kind of pattern that works for every one of these. 2 to some exponent that shouldn't be too complicated. Sometimes your formulas might have maybe a subtraction involved or something a little extra. But this one should be pretty straightforward. I'll leave some links in the description of this video about other doubling time situations and how one might go about solving those. But for now, this one's pretty basic. It's weird. It's bacteria. I don't know, but it's pretty basic. So I need to find some kind of formula. Now, the minutes past 11, that is the independent variable. The bacteria depends on how much time has passed. So I'm going to set it up so that way I have it equal to the number of bacteria. All right, that's as far as I'm going to go for here. Never mind, I got one more. So let's see if we can find a pattern. What exponent could we plug in here that follows a pattern that would allow us to get these values? So if you have any experience with 2 with doubling, which hopefully at this point you have a little bit, hopefully you've been reading your textbook and your notes and you've noticed a couple of things. You might notice this one here. This might stand out to you. 2 to the power of what equals 4? You might say, oh, well, 2 squared. 2 to the power of 2 equals 4, which is true. I said I'd use less green. Let's use purple. We just did this one right here. We took our 2 and raised it to the power of the minutes past 11, which happened to be 2, and we got 4. Let's check and see if that works for the other ones. If we do 2 to the power of 3, do we get 8? You can grab a calculator, and you should see that, yeah, 2 to the power of 3 is 8. 2 to the power of 4 is 16. 2 to the power of 5 is 32. Sorry, this looks terrible, but it's working. The math's working. And 2 to the power of 0 is 1, and 2 to the power of 1 is 2. So it looks like if we take 2 as our base and raise it to the number of minutes past 11, we get the bacteria in the bottle at that time. So our basic formula, let me erase this little square, it wasn't really doing much good anyway. Our basic formula to find the number of bacteria in the bottle after a given number of minutes is 2 to the power of the minutes, or minutes past 11 if you want to write that. I can barely write minutes, it's minutes. So if we want to find the number of bacteria at 11:37, so 37 minutes past 11, we would do 2 to the power of 37. Now, before you do any calculations, always read what the question's asking you. This one in particular is saying, type your answer using exponential notation, not scientific notation, just exponential notation, which is actually what we have here. 2 to the power of 37, that is exponential notation. So we would actually not have to go any further than that to answer this first question. Just to show you why, let's open up a calculator. Oh no, Cat's trying to help. Don't eat the pen, don't eat the pen. I love you, go away. All right, I'm gonna open up the Desmos calculator. And if you do 2 to the power of, hi sweetheart, 2 to the power of 37, we get almost a trillion. It's 1.37. Oh my gosh, yeah, that's 10 to the 6th is 1 million. 10 to the 9th is 1 billion, and 10 to the 12th is 1 trillion. So 10 to the 11th is just shy of being in the trillion range. That's pretty darn high. So this is probably why they said answer in exponential notation, because if you had to type this out, no, it just, no, hard pass. But this is a good way to approach these kinds of problems. If you are not given a formula, think it through. Try and make a chart. Try and find a pattern. When doubling time is involved, there's going to be a 2. That's how it works. And then see if you can find a pattern like we did here. I'll leave some examples in the description below, other doubling time problems, and they're all pretty similar. They're all based on that basic premise of start with 2 and find some exponent, some pattern to make it work. So we have ours. Our formula is 2 to the power of the minutes past 11 to get the amount of bacteria in the bottle. So the next question they ask is, the bottle will be blank full at that time, type an integer or simplified fraction. So at 11:37, how much of the bottle will be full? Okay, well, it isn't completely full until noon, right? At noon, which is 60 minutes past 11, is when it's full, right? So I know it's not full, obviously, because I'm only 37 minutes past, not 60 minutes past. So if they want us to type an integer or simplified fraction, a fraction would work for us. A fraction is where you can take the part and divide it by the whole. The whole, in our case, would be the 2 to the power of 60. That's when the whole bottle is full. The part we have is 2 to the power of 37. That's how much we actually have right now. So we would have this fraction here, 2 to the power of 37 over 2 to the power of 60. This would represent the fraction of the bottle that is full at 1137. This is kind of gross though, so I am going to go ahead and simplify. And I'll leave more resources about simplifying with exponents in the description. But what I'm going to do for this 60, I'm going to subtract 37 from both exponents. I can do this because 1, I am dividing, and 2, my bases are the same. So 2 to the power of 37 minus 37, 37 minus 37, 0. And then 2 to the power of 60 minus 37, that's 23. 2 to the power of 0 is just 1. And then 2 to the power of 23, let's find out. Okay, big number, but not as bad as almost a trillion. So 8,388,608. I'm not going to remember that. 8 million, that's all I got. 388,608 was it? So this is the fraction that is full at that time. That is a ridiculously tiny amount that's full, right? You can stop the video here if you'd like to. We've answered the questions. We have our formula. So no matter what they ask you for the same question, whether it's how many bacteria will there be at 53 minutes or at 14 minutes, we have our formula. It's 2 to the power of the number of minutes. And if they ask you what fraction is full, it's going to be divided by 2 to the power of 60. So we have our answer. You can totally stop and check out now if you want to. But I'm going to geek out about this for a little bit because I don't care about the bacteria part. I care about the math part. It's kind of cool. The fraction 1 over 3 would be 1/3 full. That would be if my bottle, I'll draw my crappy little bottle here. Okay, yeah, well, I did say crappy. Guess my bacteria are blue now. So 1/3 would be this much right here, right? Okay. This is 1/8 millionth, basically. So it's just like my bottle. If I were to draw this, a little less creepy. It looks like a crayon. Not on purpose, but 1/8 millionth, that's like I can't even draw that. It's so little. You'd think there'd be a bigger fraction there, but in reality, here, let me actually put it in a nice bottle that's not going to give you nightmares. Pause. Okay, here's a clip art bottle. That's a lot less unfortunate than the ones I had drawn earlier. So we said that after 37 minutes, there's like, I'll go back to green for bacteria. I don't know why. What color are bacteria? I don't know. There's like this much is in there after 37 minutes. It's a tiny amount. This is not the scale, of course, but it's just so darn tiny. Just I can't even picture that number, even though I just tried to. What's really interesting though is that if you think about it, how long does it take for the bottle to be half full? Let's pretend. Let's pretend this is half and it's just full of bacteria. How long would it take for this to be half? Now a lot of people think, okay, well it starts at 11 and it goes to noon. Halfway through is 11:30. So it should be at 11:30 that's half full, right? But that's not the case. At 11:37, it is way less than half full. Half is this, 1/2. We have 1/8 million. The bigger the number in the denominator, the smaller the value is. So 1/8 million is so much smaller than 1/2. So obviously, 37 minutes is not enough to make it halfway. And the reason is, it's doubling every minute. So if we have half here, 1/2 doubled is 1, right? And we know from earlier discussions, from my less creepy bottle, it's full at 2 to the power of 6. It's full at 60 minutes. Whoops, it's full at 60 minutes past 11. So at noon, it's full, right? It would take until noon to be full. That looks like who? Let's write out the numbers. 12 o'clock. Full. 1 minute previous. So at 11:59, it must be half full. Because then 1 minute later, this half doubles and we get one whole full. I don't know. Maybe I'm geeking out way too much, but I think it's a really interesting problem. Really interesting to think about anyways. It takes 59 minutes for the bottle to be half full. That sounds crazy to me. All right, I'm done geeking out. I will leave some resources in the description, including the calculator that I use and a link to the SSC's math page. If you have any questions, please let me know. As always, best of luck.